Okay, you handed in, I guess it's number 23. Here is my solution to 23. I suggest that you read it. Again, it's on Faraday's law of induction. And we know that the quiz on Wednesday is going to be on Faraday's law of induction. So every example that you can get your hands on would, I hope, be helpful to you in that quiz. I have some homework for Wednesday, including a problem. I've skipped G24. That's G23. G24 disappeared. G25, and I want to talk a little bit about G25 when we get to it. But I also want to talk, we're going to have quiz number 3 on Wednesday. We're supposed to have a homework session tomorrow at 9:30, but yesterday I broke a tooth. I don't know how the hell it happened, but it's sort of painful tooth. And I have an emergency dental appointment at 8 o'clock tomorrow morning. Well, if we can get done by 9:30, fine, but if we can't, then I'm going to have to just skip that. There's nothing I can do about it. I mean, my tooth is in trouble, put it that way. The lesson to be learned here is, the real lesson to learn, don't get old. Whatever you do, don't get old, because it happens. Things happen. Let me tell you, more things happen. And you see there, I have G25. Let me keep a copy of it in front of me here. And I want to say a few words about it, because it too is an example of Faraday's law of induction. This is. What this problem is let's say you have, I don't know if you would have this, but maybe in some circumstance you might. You have twin lead. You know, that's that stuff that is two wires, usually separated by some sort of a plastic so that it keeps them separated, so they don't get separated wider and narrower. It's just. And in terms of our kind of stuff at microwave frequency, it's usually what we call characteristic impedance of 300 ohms. And that 300 ohms is set by, well, the diameter of these guys, but let's say not minor influence. The important thing is the spacing. The spacing dictates both the L, the inductance per unit length, and the capacitance, as you might expect. It's a capacitor. It just happens that this isn't a plate and a plate, it's a wire and a wire. So there's a capacitance per unit length, and there is an inductance per unit length. And that's dictated by the width, primarily, between the two. And they make it, for our purposes, let's say for television, going from your antenna to your television, 300 ohm stuff, all right? But you can have other ones too. What you don't want is you don't want to make these too close. In other words, you want to do that. The reason for that is because then that characteristic impedance might, instead of being 300 ohms, might go to 1 ohm. Well, that might be kind of hard to match at the other end, or to the piece of equipment you're trying to deliver power to or whatever. So it's not too practical to make them real small. This has something to bear with on my problem. But anyway, we have this twin lead, a transmission line. Let's say I'll draw it in 3 dimensions, like so, like that. And of course, it might be a telephone line. And so you have essentially a signal here, and then of course then you have a receiver here, and you're leading one to the other with this transmission line. Now, the difficulty that I presented in this problem is, oh, by the way, that transmission line, which might be, several miles long, is right near a transformer. And that transformer creates a B field, like so, and that B field is at probably 60 hertz. If this is a 60 hertz kind of transformer on top of a pole someplace. And so we have this B field fluxing through the area between, in other words, this area, there's a B field. And guess what? I mean, it's kind of like a big long loop, and through that loop is a time-varying B field. Guess what that does? It induces in here, Mr. Faraday says, I'm going to induce, in addition to your signal, this is the voice you're trying to hear over here, in addition to that, there is also, plus to minus, a voltage, an EMF, which is undesirable, and that, whatever is undesirable, we call noise. It doesn't necessarily mean it's that kind of noise. It might be a hum or something like that. That's probably what would happen if this was at 60 hertz. But that's undesirable. So you hear this hum, and then in that hum you hear this voice. Well, you'd like to get rid of this if you can. And one way to get rid of it, obviously, is to say, oh, well, that thing is on the telephone pole. Let's move this thing way far away so the B field is really weak. And yeah, that would do it. But it might not be practical. I mean, you got this telephone pole, and the line is strung on the telephone pole. You wouldn't have another telephone pole across the street or anything like that. So that might not be too practical, right? It's a solution to try and reduce this, but it's not a good one. Then the other one was what I alluded to. Hey, make that area really small. I mean, make it a skinny, skinny loop so that it's like this, and then you don't get much B field, not much flux fluxing through there, so d phi dt is small, and yeah, that's another solution. But I told you, that makes the characteristic impedance of that line perhaps impractical, okay? So then it's a solution, but an impractical solution. So then what I ask you to do is a third solution. And that's the one I want you to work on. And I give you a hint. The hint is that when you get that flux, it's an integral all over the B field dot ds, right? This is equal to the flux, the B, so many Webers per meter times the number of meters gives you the number of Webers going through there. And then the voltage is the rate of change of that with respect to time with a minus sign in front of it and all that. Yeah, this is given to you. I mean, that's the transformer on the pole. There's nothing you can do about that. Well, I suppose you could not have it there, but let's say AEP won't let you do that. So this is a given. So the only thing you have to play with is that, to make this small so that this is small, so this is small. Okay, this noise business is small. You understand that? So the question is, what is it that you're going to do to this ds in order to have that third solution, which is practical? Okay, and I'll end it there. But that's what this problem is about. Somewhat practical. Okay. Okay. This will be this quarter, this semester will be my last quarter of teaching. After I retired in '95, I've been teaching essentially for nothing for 17 years. That's a pretty long stretch, I would say, to be donating my time, but I enjoyed it enormously. And the students I got to know during those 17 years are just, there's no comparison. There's nothing I could have done better. But everything has to come to an end. I'll be almost 80 years old, and maybe I'm at the end, pretty close to, teeth are falling apart. Had to get hearing aids. I had, my eyes were getting trouble with cataracts. I'm falling apart, face it. The brain is still working okay. Knock on the table. But anyway, the last lecture that I will be given in this court will be December 3rd. And so I don't have that many more lectures to go. And what I'm trying to do is get rid in my office of things. Matter of fact, the chairman says, you damn well, you better get rid of things. They're going to use my office for something else. And I found over the years, I always give pictures of those two important guys. I mean, Mr. Faraday and Mr. Maxwell. Now, I don't have enough of them to give to everybody, so if you plan to throw them away or use them as toilet paper or something, I don't want you to take them, because I only have a limited amount of these left over toward the end of my career. All right, I've always given these out over those 17 years, and this is what's left. Nice pictures, and they're particular. Now, this is Faraday, handsome dog. He was about 30 years old when this picture was taken. And it was about, this was about the time when he was thinking about that Faraday law of induction, 1831. He was born in 1790, so that would make it around when he was 31 years old. And that's where he is, right here. And there is a battery here because apparently, you know, he put some currents through and closed the switch and opened the switch for a transformer and found this law of induction. That's Mr. Faraday, Michael Faraday, very important guy. If you really appreciate your discipline, he is a founder, really, of our discipline. So somebody, if you, I don't have enough for everybody, unfortunately. Then the second one, this is James Clerk Maxwell. It's spelled C-L-E-R-K. That's the way it's spelled, James Clerk. But the British don't say that. They say Clark, James Clerk Maxwell. And here, you always see James Clerk Maxwell as an older man, not real old, because unfortunately, he was born in 1831, the very year that Faraday did the business of Faraday's law of induction. Can you imagine that? So he was born that year. And unfortunately, he didn't live very long. He died in 1879, at the age of about 49, something like that, 48, 49, not quite 50, of cancer of the throat. Unfortunately, if he had lived longer, he would have overlapped with Einstein, and who knows what the hell that would have led to. But this picture is nice because at this picture, he's not got a big beard, and he's not an older man. He's a young kid. He's 21 years old here. He's a senior at Cambridge University, just your age. And he was already doing experiments. I told you, he did lots of things. One of them was he was interested in how human eyes see color. And this is his so-called color wheel. When he first graduated from Cambridge, he came from a wealthy family. They lived in a big mansion outside of Edinburgh. He was born in Edinburgh. And the money came through his mother's family. But they lived and he was sort of a farm boy. I mean, he was a great horseman. He liked animals, you know, sort of a, and when he went to University of Cambridge, which was very sophisticated, all these highfalutin guys there, the sons of everybody there, and they considered him to be sort of a bumpkin, you know, sort of like his clothes weren't right, you know, all that kind of stuff. Anyway, and they called, his nickname was Dafty, because he was a little daft, I suppose. He was a nerd, face it, he was a nerd. He was thinking thoughts way beyond what these kids were thinking of, his classmates. But anyway, there he is at 21, your age, already doing experiments. When he graduated, his father built onto the mansion a wing and for his laboratory. He didn't have to go to work because the family had some money. And as a matter of fact, his father wanted him to go, as all rich people did, go to Oxford, you see. But he was interested in science, so he wanted to go to Cambridge, where Newton and all those famous people went. So the father says, okay, we'll do that. And not only that, but he must have been a very liberal father, because he built him this special wing, and he did his experiments there on light. And then he tested all of his friends and his parents' friends and everything for how they saw light. Now you got to realize that was a big problem in those days. Across the channel in Germany, the German professor, what was his name? Kirchhoff, I think. I'm not sure what his name was. Helmholtz. Professor Helmholtz was doing all sorts of tests on how human beings see light and color the different parts of the spectrum and so forth. So that was a popular problem at that time. But then, you know, here this Faraday guy, when he was born, came up with this Faraday's law of induction. Gosh, interesting. When he was then, he was a little older than this, and when he was 24 years old, that would have put it 31, 41, 51, 1854, he wrote his first paper. He wrote his first paper on how this Faraday's law of induction might work. It was, and then he wrote another one about 3 years later, which was more detailed, but still, he was trained mechanically. In other words, he was trained as a hydrodynamicist. He was a great mathematician because of that, because the math required for hydrodynamics was pretty deep. So he knew all about curl. He could actually think in terms of the curl and fancy things like that. He was a mathematical genius as well as a physical genius from physics. So about 1857 he wrote a paper, but the paper was all mechanical sort of stuff. He had rolling wheels, sort of like little rollers, and then the little rollers drove little cogwheels, and those little cogwheels turned other rollers, and then these rollers were supposed to be proportional in their speed to the strength of the B field, and then the if this roller wasn't going quite as fast as this roller, that little idle wheel would move a little, and that was supposed to be sort of like the current that's in the metal that this is supposed to represent, and stuff like that. That's what he was doing. And then finally, in 1857, 1864, 65, I think, he wrote the real paper. He did away with all that mechanical stuff, and then it became ununderstandable. Most people could not understand all this vector stuff that he knew all about. And so he wrote it in a way that we would not recognize today, simply because he felt maybe these people will understand my vector stuff this way rather than the way we study it now. But he took away all that mechanical scaffolding, and that was the great paper. That is the paper where he said basically that magnetics, electrics, and light are all the same phenomenon, and actually that light travels at the speed which we know is equal to 1 over the square root of epsilon 0 mu 0, all that kind of stuff. That's what he did in that paper. He wrote a book. I have the book in my office. He wrote a book based on all of this stuff. And don't forget, in the meantime, he was doing all kind of the theory of gases and stuff like that has nothing to do with our electromagnetics. So a genius of the first rank, one of the best physicists that ever lived, is this guy here. And here he is when he was 21 years old, just starting out. So give you a little encouragement. Great things can happen. So take that and see if you're interested in keeping a picture of Mr. Maxwell. And of course, when I got my dog, I had to name him Maxwell. I mean, I just had to name him Maxwell. So that's good. I was thinking maybe I should bring Maxwell here. I mean, during this lecture. Maybe I'll lecture, I won't finish with Maxwell today, so maybe I'll bring him next time when we have our exam. He can bother you while taking your exam. Okay, speaking of bother, here, why don't you take that? Okay, all right, let's get to it. Well, I'm not quite to Maxwell yet. Not quite. Because what I want to talk about is still Faraday's law of induction. And I remember when I was your age in college, the physics professor, not electrical engineering professor, the physics professor, we went to a different building, the physics building for our course, had a interesting gadget. Basically, from the ceiling, tall ceiling, he suspended a pendulum. So this is, and then the pendulum held a plate of aluminum, something like this. Just a plate of aluminum, and then this was pivoted here. And then that aluminum plate, if you looked at it end on, so here is the pendulum, and here's the plate, he had a permanent magnet, or actually I think it was an electromagnet, you know, one of these famous U-shaped things, so that we had a B field going across here, right? A B field. If he put the current on, then there was a B field. If he took the current off, it wasn't a permanent magnet, then this was no longer a North Pole, South Pole, so the B field went to 0. So he could control whether there was a B field here or not a B field here. And then what he did, so I'll just picture that as here is the pole of the magnet, and there's another pole on the other side, and there's the magnet and the coil down there. And he had a switch, and he turned it on or off. DC current. And then what he did was, with the current off, meaning the B field was equal to 0, he took this pendulum and he lifted it, and it swung through the region between the two poles of the magnet. And it just swung there. I mean, that's what it did. It just kept swinging like that, pretty long. I mean, the period wasn't very long. I think it goes as the square root of the length or something, the periodicity. Anyway, pretty long from the ceiling. And that was fine. And then what he did is he lifted it up and he turned the B field on by putting current through here. And that pendulum came along, I mean, swung, and bam! It was almost like it hit a concrete wall. It just, boom, stopped like that. Boy, that was interesting. And then what he did is he said, let's take that plate off. It could be unbolted. And he put a plate on that looked more like this. I'll have to draw it with cuts in it. These are cuts like this. Those are supposed to be cut. So there's metal and then gap, metal and gap, metal and gap, all the way around like that. And then he did the same thing. He had the current on, so there was a strong B field here, and that thing swept through just like that. So of course he wasn't talking about, like, okay, explain that, you know, explain this stuff to me. Well, of course we couldn't. We didn't know what the hell was going on. But then he explained what was happening. When this plate, when the B field is not there, there's nothing happening, of course. But when there is a B field here, and there is a, guess what, velocity, the B field is constant. So this is the case where if you look at it from the Lorentz form, that first term, there's no rate of change of B with respect to time. That's gone. But there is the velocity term, V cross B dot dl. Like that. So what was happening was, let's say in the solid plate, when that velocity was moving along, there was voltage induced in here. And this is one of those ones where I said that you don't choose the path, like in a wire, where you choose the path of the current. Mother Nature chooses the path. She chooses a path, and she probably chooses, you know, some kind of paths like this, like that, induced by a voltage that's induced in that path. But of course, it's all over, and we might represent it like this. So Faraday would say, Lorentz would say that there's a voltage induced in here, and that voltage is going to cause a current, and Mother Nature will choose the exact path of the current, fine, but you do have a current flowing in here. And then, after that's established, and it will happen, then you refer to Mr. Ampere. Oh, a current flowing in a B field. Oh, Ampere's force law, right? The current crossed into the B field is going to be equal to a force. And it turns out that that force is a retarding force. It doesn't, as it swings through, it doesn't accelerate it. What it does, it slows it down to the point where it happened so quickly that it was almost like hitting a brick wall. It didn't like slump down. It really jammed in there. And so we have a wonderful example of Faraday's law of induction and Ampere's force law, both in this very simple device. Now you might say, oh, well, that's a cute little device. Oh, and by the way, then if you cut slices in here, what are you doing? It's kind of like you have a circuit, and you put a battery on there, well, an EMF, and then you have a high current running around, and that's the high current that causes the forces of Ampere. And then what if you said, oh, I think I'll put a gap, and a gap, and a gap, and a gap. Well, then no current will flow. And of course, that's what's happening here. This current has difficulty going across that gap and that gap and that gap. So what you've done is you've done away with these currents. Even though there's an EMF, the impedance is so high because of the air. You see what I'm saying? So that's how it breaks. Now these kind of currents, if you take a look, they kind of look like that. That looks like what? If I was watching, if you had your bathtub full of water and you pulled the plug and you watch the water circulating around, it's like a whirlpool. It's called an eddy. That's an eddy of water. And that's what this is called. It's called eddy currents, E-D-D-Y, eddy currents. And what you're doing is you're breaking up the eddy currents. Now I'll give you another example. Here is, and this is more practical, this is just a toy, but here is, again, am I drawing this right? Anyway, this is the iron core of a transformer, and here is the one, here is the other one. Remember I was talking about, you excite this one, you get an H field running around here, and if the mu is big, then you get a gigantic big B field, and a big B field, rate of change is going to give you a nice voltage at the output, all that kind of stuff. So this is iron, a wonderful conductor too, it's copper, but a good conductor, and you have this B field. B as a function of time. Now this is the case where the B is a function of time with no velocity. This is the transformer part. This is the first term in Lorentz and not the second term. Now, and it's in metal. It's in bulk metal. So Mother Nature says, oh, hey, you got a B field? There's a voltage induced. And I'll picture it maybe colored. There's a voltage induced in me, and I'm going to cause a current, and I'll picture it like that. And so if this is the cross-section of the iron here, and here is the B field fluxing through. What's going to happen is you're going to have a voltage induced, and it's going to cause a current perpendicular to the B field. There's going to be a current, and a current, and a current. Those are really eddy current, they call them eddy currents. It won't be just one, it'll be a little one and a big one and a big one like that. Eddy currents running. And of course, the B field is, this is probably going to be, let's say, 60 hertz. So the B field first this way, then that way, then this way, then that way. So the current is like this, and then it's like this, and then it's like this, and then it's like that. Okay? In iron, which isn't the best conductor in the world, so guess what's going to happen? Current flowing through a reasonable conductor is going to give up heat. The core of the transformer is going to heat up. Where does that heat come from? Oh, it comes from essentially the energy in, and then this is going to give energy, heat, and so by George, the energy out is going to be equal to the energy in minus the energy heat. And what you'd like to do is make that as close to zero as you can. You can never make it real zero, but right, you want to make it an efficient device, getting the energy at the primary to the energy at the secondary. And if you got these damn eddy currents, and those eddy currents aren't just here, but they're all the way around, you know, where that B field is. So they add up. So how do you reduce the eddy currents? Same way as you did here. What you do is you don't build. You will find if you take apart a transformer, it's not built of a solid chunk of iron. You know, first of all, that's expensive to do, has to be cast. What you do is you find that it's made up of plates. So here's just a thin plate, this side, this way, and then there's maybe a certain thickness, and then another plate of the same, another plate, and they're separated by varnish or some non-conducting thing, right? So you have this plate after plate after plate. If you take a look at a transformer and you look at it end on, you'll see these layers, okay? That's what it is iron plates separated by a very thin, some sort of non-conductor, like varnish or something of that sort. And what all that's doing is that now, when the eddy current tries to flow, I should make it green again, when the eddy current tries to flow, it sees open, 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 open. It sees open circuits, and it doesn't, there aren't very many eddy currents. If there's not many eddy currents, then you don't have much heat going on, I squared R. And so this is maybe not 0, but it's approximately equal to 0. Isn't that neat how that works? So this little toy says it. And this is a practical example of it, and you'll find all transformers are built that way, both for economic reasons and because of the eddy current business. Then the other thing is, you know, here, and in here, for example, when that pendulum, let's say you didn't have the cuts, so the thing, you start out with, guess what, kinetic energy, right? There's a lot of energy in that baby. There he goes, mv squared or something like that. Isn't that that's the energy that this fellow has, mechanical. And then suddenly it stops, and the mechanical energy went someplace, right? It didn't just disappear. It went into heat. That's what it did. It went, boom, into heat. All right? Now, wouldn't it be neat if somehow in this device you had some way, there's a voltage induced and there's a current like that, if you had some way of taking that kinetic energy and instead of turning it into heat, you would essentially take that energy and charge up a battery or something with that. You do that. And if you buy a Prius car and you step on the brake, that is exactly what you're doing. You have a system somewhat similar to this, but instead of those eddy currents just being lost in heat, which would be a waste, what you do is you find that current and the voltage across some terminals, I suppose, this is all proprietary to Toyota, I suppose, but that energy goes back to the battery, and you are, as you're stopping, you are charging up your battery. Isn't that neat? So you're not wasting the energy. Like when you have regular abrasive, you know, like disc brakes or something, it's going into heat, and that's it. That's the end of it. It's just going into heat, and you're not using it. This is reusing it, so to speak. So it's a very efficient way to do things. So, I mean, we're talking nifty stuff here. That's why those two guys, Maxwell and Faraday, are super critical to your whole discipline. That's the way almost everything works, to tell you the truth. I could talk about antennas. How does a voltage, you got these two wires. You got a wire and a wire, let's say. And you hook this, maybe with twin lead or something, to your TV. There's a voltage across here. Where the hell did that come from? I mean, there's a wave coming along. This is an antenna, a dipole antenna. This voltage induced in here, you can think of it as, there's one of these, the induced Faraday's law of induction, right there, Faraday's law of induction. And we're talking about much higher frequencies, the 60 hertz and stuff like that, but it's the same old, Faraday's law of induction. Everything works in Faraday's law of induction. Or Ampere's force law, that's how motors turn and all that stuff, right? Dynamos work on Faraday's law of induction, or generators, or alternators, or whatever you want to call them. So do respect those as being your founding fathers, please, of electrical engineering. Very important guys. And did I have a question way in the back?
I had one earlier, but I think you kind of went into it. But what if, so as long as there is some path for that current to go, it would stop?
Yeah.
So what if...
Because of Ampere's force law, because there is a current and there is a B field. Yes, okay.
Does the intensity of the B field or the diameter of the pendulum have any effect whatsoever?
Oh, well, he only had one. It was probably maybe 18 inches by 18 inches, this thing. He never did a little one, but I suppose, yes, I suspect that if it was a little guy, then there would be currents in there, and maybe it wouldn't go boom, but it would go, you know, sort of slug in there, you know, probably so, because the force wasn't as strong going back.
So it wouldn't be like, I mean, if it were a smaller thing, it wouldn't be like, you know, a child swinging on a swing and the feet dragging. So if
it was small, it would probably go
okay, yeah, that's
like that. That's probably what would happen. Whereas when he had no B field on there, it just kept swinging, you know, it wasn't damping hardly at all.
Okay.
So it would add damping. Now, how the Toyota works, that when you put the brake on hard, it stops it quickly, and you would put it on gently. I don't know how that works, and probably you can't find out because it's proprietary.
You could do it in the motor controller.
What's that? Maybe in the controller.
They have,
yeah. Yeah, he knows all about that because he's a big car guy. Hey, you should give a lecture on that.
They have a really cool system for it. It's nifty.
Okay, he knows a lot more about it than I do. But anyway, that's basically how it works, right? I mean, that's the real thing. So all you're doing is you're changing your wheels from motors to dynamos, I guess. That's what it amounts to. Okay, and the dynamo is feeding a battery rather than a resistor. Okay, all right. See, I'm not even to Maxwell yet. Just more examples of Faraday's law of induction. These eddy currents, they call it. In my notes, I have quite a few pages actually devoted to a wire with current flowing through it, copper or whatever it is, and how much heat goes up in it. And then I have an analysis where if you break that copper up into little wires, like this, and there's a certain packing factor and all that stuff there, how much do you save on eddy currents? In the first case, where there's a B field, you would have eddy currents and you give off a lot of heat. If you break up the eddy currents up by having little wires, you reduce it by quite a bit. I think it goes as the number of number of little wires squared or something like that. I have a whole analysis of that in my notes. It's the same old as what I just talked about. Okay. Now I want to do one more thing before I actually hit Maxwell, although this is a transition into Mr. Maxwell. I'm going to write this down. You should recognize this as a Lorentz form of Faraday's law of induction. C could be a function of time. This S, C could be a function of time, and all that things is dot DL. So let's just write it C, and let's write it S, C like that. Now, what I'm thinking of is, okay, let's say I don't have any wires or anything. I'm here in the middle of the room. Do you see any wires? No. Do you see a B field that's changing with respect to time? Well, you don't see it, but it's here. I mean, radio station, there's light. There's all kind of stuff going on. Electromagnetics, right here. No wires, though. If there's no wire, like for example, let's say I take this air wire right here and I move it. Well, does it make sense to talk about nothing moving? I mean, there ain't no wire there, so how can you move it? That's the answer is you can't. So basically, for that analysis, so let's say we are in free space or in stuff all over free space, but let's say see free space. Then the velocity has to be equal to 0 because it isn't there. You can't move something that isn't there. So then this term goes out. So we are left with, from the Lorentz form, we have the voltage induced is equal to, in this loop, which is air, but you can't move it, but so that term is 0, but you can have flux going through it. You can do that. And then therefore you can have a voltage induced, and that's the voltage induced. I told you that even without any metal there, you can have a voltage induced. Now it's hard to pick that voltage out because the impedance here is so high. Remember I talked about that. But you do have a voltage induced. That's this guy here. Now the minute you got a voltage induced, we learned way back that a voltage can be written as an integral of E dot dl all the way around some sort of a contour, right? I mean, volts per meter times the number of meters is the number of volts. So this is an alternative fancy-dancy way in terms of the field that is induced around here due to that and I'm picturing it at one place, but don't forget that thing is all over the place, all around like that. And then that is equal to minus this integral partial of b with respect to t dot ds. So that integral is equal to this integral. Well, I mean, one is a line integral, just one of these, and the other one, and this is SC, this one is a surface integral. So guess what do? I use Stokes' theorem. Stokes' theorem makes an identity. It's just mathematics. But it's an identity that says, oh, that guy is equal to the integral, or the surface that is surrounded by that C of not E, but the curl of E. If you recall, like that dot ds. And then that's equal to this surface integral. And maybe I should put the minus sign inside here. And then if you say, well, which of these, was it this one, or was it this one, or that one? So any, again, any is very important. If anyone and anyone are the same, and that's here, then you can say that the integrand, the integrand is equal to the integrand. So from that, I come up with the curl of E is equal to, it's not equal to 0. Remember, when it was a steady, independent of time thing, I would call it that kind of symbol. Now, technically, I should write it like that, but the fact that it's script means, hey, it's a function of time. This was not. This one is. It can be a function of position, but it's a function of time. So if you want to leave it like that, fine. It's not equal to 0, but it's equal to minus the rate of change of b, which is a function of time with respect to time. Look at that. And that essentially is a statement of Faraday's law of induction at a point. In other words, right here, I have a B field that is changing with respect to time. And because it is changing with respect to time, I have to have an E field changing with respect to time. I have no choice. No circuits. I'm not talking circuits here. I'm talking strictly what's happening in this room. Okay? So if you put a paddle wheel in this kind of a field, it wouldn't turn. And remember when it was 0, I don't care where the hell it's oriented or where you put it, it's just not going to turn. Here it will turn because this is not necessarily equal to 0. Now if it is equal to 0, then this is either a static field. I mean, if this is 0, then either it's this thing or that thing is 0. There is no field. Okay? Or how would this be equal to 0? Well, if B is a constant, for example. So I would have a magnetostatic field. Let's say that was a constant. B is equal to 3 Tesla or something like that. The rate of change of 3 with respect to time is 0. So this would be 0. And then, therefore, you have some sort of an electric field, but it is static because this is 0 here. And you would have a static field and a static electric field, and you'd have a static magnetic field. It'd be kind of like, oh, I had a coil of current running around causing a B, which is static, like this. This is a DC current. Let's see if I got it right. Yes, it's coming out and going back in the back end there. This is a constant B field. And then, oh, by the way, in the vicinity I have a couple plates with a Q and a minus Q, and that causes a static electric field. You could have that. But they are totally decoupled from one another. This B field knows nothing about that, doesn't care about that, and this doesn't care about that. But the minute you start making this current dynamic, and therefore this turns into one of these, oh, well, now there's a connection between that B field and that E field. Then you have an E of T. Maxwell's theory. That's what Maxwell said. If you got one, you got to have the other. If you have the other, you got to have the one. One causes the other. And they go according to his laws. We're only at the first law. This equation right here, is called essentially Maxwell's first equation. But really, it's Faraday. And so I like to call it the Maxwell-Faraday law. This is the Maxwell-Faraday law because really, Maxwell wrote it fancy-dancy, but Faraday was the guy who thought the deep philosophy behind it, okay? And Faraday, being a sixth grade guy, didn't have any mathematics, but Maxwell was a super mathematician, so he could mathematize this stuff with curls and all that fancy thing that he knew about from hydrodynamics. So this is Maxwell's first equation, or I call it the Maxwell-Faraday equation. And it is in differential form. You know, this is a differential in space and in time. This is the differential form. I will talk about integral form. We already do have it, but this is the form that we're going to be dealing with. Okay. Now let me point out at this point, when Maxwell was doing this in the early 1850s, when he was in his early 20s. I mean, he was about your age. Can you imagine he was doing this kind of stuff? Now, at that time, when he was that young, I don't suppose other great physicists really knew about him. I mean, he was in England and Europe, you know, Germany and all that were the center of science at that time. But eventually, Maxwell got to be known as a pretty important person. And it turns out that all the great scientists of Europe, except Maxwell, didn't believe in Faraday. They didn't believe in this field idea. There was this field idea, you know, the charges are all important. To hell with this field business. They poo-pooed that. I mean, poor old Faraday. And he said, you know, I got my PhDs. I got 3 PhDs. What was this guy from the 6th grade telling me what to think? So it didn't go over very well, except when Maxwell got on board and says, I think he's right. I think the field is important, and I'm going to work on it with my mathematics. And he came up with this kind of idea, all right, this way of writing things. And of course, when the great Maxwell spoke, everybody had to perk up their ears. I mean, they had to. So that was the beginning. Now, those two guys never met. They were both in England. One was a Scot. Maxwell was a Scottish guy. And Faraday was born in London, an English guy. But they never met. Sort of surprising, actually. But anyway, so Maxwell was a backup for Mr. Faraday's ideas. And because he was so powerful, people had to begin to rethink their own thoughts on this subject, including the mathematicians. And there are all kind of arguments between mathematicians and physicists about this stuff. Okay. All right. Now I'm ready to launch into Maxwell's 4 equations. He has 4 equations. We have 4 equations. We have this. The electric world. Remember, this is how the field is connected to the mother source. And this is the property of the field if you realize that D is equal to epsilon, let's say we're in free space, epsilon 0 E. So that's off to the side, that's called the constitutive relationship. You write that off to the side. But this is the property of it. It's called conservative field, right? Or it's called a laminar field, right? Or it's called a curl-free field. Depends what kind of discipline you are in. But this connects the field to the source of the field, and this describes the field. Then in the magnetic world, we had and that was, you could call this Gauss's law. This looks like Gauss's law too. Sometimes they call it Gauss's law in the magnetic world. This is Gauss's law. We don't even talk about electric. But this is also, this says no magnetic monopoles. This is how, essentially, the character of the, and we call it solenoidal. You remember, it eats on itself. It's called divergence-free or no magnetic monopoles. Again, 3 ways of describing it, like 3 ways of describing the character of the E field. And then how is the B field connected to its mother source? With a mother source being DC current now, for us DC current. It's called Ampere's circuital law. something like that. And here is the source of the magnetic field. Here is the field. This is the description. And then off to the side, you write, oh, by the way, B is equal to mu 0 H. That's the constitutive relationship. Remember that? All that stuff. And this world was separate from this world. I mean, they had nothing to do with one another. Now, what Maxwell said was, oh, hey, I'll erase these constitutive ones. He says, oh, hey, look, Mr. Faraday says, and I mathematized it, that it isn't equal to 0. When this thing is time varying, then this isn't equal to 0. It's equal to minus partial of B with respect to t. And he accepted that. In other words, he believed in Faraday. So this is the Maxwell-Faraday, what I call the nobody calls it that, but I like to honor Faraday too. That's really Maxwell's way of writing Mr. Faraday's theory, okay? And it is definitely not equal to 0. Well, look at that. Here's the electric world with the magnetic world thing in it. It's already coupled to this world, okay? So then, what Maxwell said was, I believe this. This is what we will call it his first equation. He says, I also believe in Gauss's law. And he says, I not only believe in Gauss's law, but I believe it when everything is time varying. So we would write it like this, and you would maybe use the same symbol. We'll remind you, oh, hey, that charge is now a function of time. So here's the cloud of charge, and it's moving, or it's jostling around, or it's pulsating, or something. It's a function of time now, okay? Not like before, where it's just steady. He accepted this. So I would call this Maxwell-Gauss, okay? Again, honoring Gauss, because that is Gauss's law, and he accepted Gauss's law. He also accepted this, which would be Gauss's law in the magnetic world for time varying. So B is a function of time. See, all these script means functions of time. I won't write it explicitly. So this would be Gauss's law for the, or no magnetic monopoles. And what he was saying was, well, if there's no magnetic monopole, I don't care if it's steady or if it is time varying and pulsating or whatever, there ain't none. So this is going to be 0 all the time. So this would be Maxwell, no magnetic monopoles. Okay, no north poles all by themselves. That's what he was saying. And I accept that. So basically, he accepted Faraday, he accepted Gauss, he accepted the physics of no magnetic monopoles. And what the hell did he do? I mean, we're already 3/4 of the way there. Well, what he did was, and the guy has squeaked, but what he did is he found fault with Ampere. This is Ampere's law, plain old Ampere right there. And one of the problems he had, I'll name 3 of the problems he had. The one problem is he saw in the electric world a term that comes from the magnetic world. He looked at the magnetic world and he saw no comparable term of the electric world. He didn't see any E or D or anything here. And those guys, and you too should, always were sensitive to what we call symmetry. In other words, he was thinking, there should be something to do with D or E or one of these things up here in the magnetic world. He did not see symmetry. He didn't like that. The other thing, which was much more serious, that's sort of a feeling, but much more serious was, he says, I'm going to test this guy and see if this equation is consistent with conservation of charge or the equation of continuity, and it wasn't. And that was serious because he believed in conservation of charge. You can either make it, or you can move it from here to here, but you can't make it or destroy it. So then that was, and then the third objection he had was, I do not understand how a capacitor works. Meaning that here I have a wire, and here I have a plate and another plate, and I got current flowing in that wire, maybe AC current, and that same current is flowing here, but there's none flowing here. I mean, there's no current there. How the hell, how can that work? He didn't understand how a capacitor could work. So, and yet it worked. So he had to explain that. And so what he did is he added a term to this. It's going to be the rate of change of D with respect to T. We'll talk about that more. And that solved all three objections that he had. And that would be then called the Maxwell ampere. And I will talk about that equation next time more carefully. Okay? That's it. All right. We will see you on Wednesday. I haven't made up the quiz. I unfortunately am canceling maybe I'll be done with that dentist at 9:30, but I can't guarantee it. My tooth is very important, so.
If you have a contingent that shows up